Hello, hello everyone. Today we discuss about Laplace transform, one of the integral transform machine in mathematics, which is very powerful transform machine, especially in solving differential equation generally with initial value problem. So here in this section we are going to compute the Laplace transformation of certain functions before we deal the basic property through definition. So the Laplace transformation is one of the advanced operations beyond the elementary operations, addition, subtraction, division, and multiplication, which is crucial in nature to deal in mathematics. So given a function f of t for t equals to 0, the Laplace transform of f of t is given by Laplace and L characteristic of f of t. We read Laplace and f of t, the L characteristic, so that from 0 up to infinity, f of t is minus sct dt, where the real part of s is positive. Might be a complex number here, so that we consider the real part to be positive. Optionally, we represent Laplace of f of t as big F of s to distinct from the original function here. Here is the original function through this operator. We obtain big F of s. New transformed function of s would be obtained using the improper integral here, so that if this improper integral converges, the function has a Laplace transformation, means the Laplace transformation exists in a sense. Now let's see, using the definition for a function, if f of t is 1, then Laplace of f of t means from 0 up to infinity, f of t raised minus sct. This is the definition for any function f. F may be g may be h, and so like. It might be a function of t, function of x, a function of y, and so like. It doesn't matter. It might be any independent variable, so that we use this function. So for whichever you have been encountered, any function f of t, so we use the definition from 0 up to infinity, then the function itself, then e raised minus sct dt we mean. So in our case, we have f is 1, so from 0 up to infinity of 1 e raised minus sct dt. Then from 0 up to infinity, 1 times e raised minus sct is e raised minus sct. Then we look for integration here, e raised minus sct, using substitution, letting minus sct, this power is u, then du mean minus 1 over s dt we mean, so that we have this form we mean after making integration. Obviously, throughout our discussion, most of our task is involved with the integration, so that I highly recommended you to revise the integration techniques you have been dealing in undergraduate or in applied mathematics 1, 2, any form, in any section or calculus, in any form of the courses you have been taken, so that it will not be difficult to use such forms, so that we don't perish our time in computing the integrations. I skip a big chunk of the work here. The only thing I will show is certain difficulty of integrations here. That's why as t goes to infinity, this e raised minus sct tends to 0, because if s is restricted to positive numbers only, unless the improper integral diverge. Okay, that's why we restricted. As t goes to infinity, e raised minus sct is 0. When we have 0 here, minus 1 over s, we move it out, so minus 1, so Laplace of 1 is 1 over s, where s is positive. So for Laplace of constant number 1 mean 1 over s, where s is positive. Now let's look at for other forms of functions, like the exponential functions here. We have the function e raised at t, then Laplace of f of t mean from 0 up to infinity as usual. By definition, we look at for definition of the Laplace transformation of an exponential. So that's from 0 up to infinity of e raised at mean e raised at e raised minus st dt. Again, we sum up the exponents due to the symbols here. We have the symbols. This is the symbols. So that we have a format of e raised at e raised minus st. After we sum it up, we get this term. Now we seek an integration for this integrand. Again, it would be calculated using the substitution letting a minus st is u. That's extremely elementary, the substitution techniques. Then finally we get this, the indefinite integral. Then you have to be assigned a specific value at t goes to infinity, as t goes to 0 again. If you assign t goes to infinity, mean this term, the numerator term tends to 0 if a minus s is less than 0. Otherwise, the diverge means so that the Laplace transformation of this function do not exist. That means we have e raised minus a minus sct, so that the Laplace transform doesn't exist. Mean we are not seeking for Laplace transformation of e raised. That's why we have highly restricted to s is positive. If t is 0, we mean we have e raised 0 is 1, so 1 over a minus s minus 1 over a minus s mean we reshuffle the terms in the denominator so as to have 1 over s minus a, where s is positive, greater than a. You mean s minus a is less than 0. S minus a is less than 0. a minus a is less than 0 here. I'm sorry, because we have already discussed it here. We just mentioned in this term to be exist the improper integral. So for any exponential Laplace of e raised at mean 1 over s minus a. In particular, a is any number, so that you can plating inside it, whichever you have been plating a, then it has a form of 1 over s minus a mean. Let's say in particular, if a is 1 in here, that means e raised 1t mean 1 over s minus 1. Again, if a is 3 mean minus 3 mean, so in place of a minus 3, they tend to be plus 3, so 1 over s plus 3 you mean. So that's most of the time our task is involved with the integration technique. We have also f of t, then Laplace sign of t mean from 0 up to infinity t raised minus st dt. By definition, we mean whichever you have, we use this formula. Then Laplace of t mean, this can be computed using various mechanisms, but here to tackle this integration, let me use the tabulation method here. This column indicates the differentiation to get 0, then we posit it after we have catched up the 0 differentiation. The 0 term, again, this will be the column to indicate the integration. So we have t raised minus st listed in this form. So this differentiation is 1, this integration is here, again 0, the integration is this. Using substitution technique, the second column will be resulted. So we should not be clear on after we get 0 here, so that this plus or minus, again, the coefficients of the products. So we have this form, the indefinite integral will be using the tabulation method is resulted. Then finally you assign to t goes to infinity, t is equals 0. So since we have each term have e raised minus st, if s is positive, so this term tends to 0, this term tends to 0 as t goes to infinity. So the whole thing makes 0 here. That's why 0 minus 0. Minus here with this better, as t goes to 0, we mean we have 0 here, 0, again 0 here is 1, e raised 0 because 1 over s squared. So finally, Laplace of t is 1 over s squared. In the same fashion, you can also compute Laplace of t squared e raised minus st. Again, this can be break down using the tabulation method. So let me skip a bit chunk of here, which is more similar with this. One more term, only t squared e raised minus st. So we find this, then you seek to assign specific value for t is infinity, t is 0. Then Laplace of t squared is 2 over s squared. The same fashion, again, you can compute Laplace of t cubed, t4, and so on. Finally, we have Laplace sine of t the power of n mean n factorial over Sn plus 1, where n in this case indexed from 0, 1, 2, 3, 4 integers. But it works again for any function, because you can set up as a gamma function what n factorial we mean. You will see in the other videos if you subscribe it, obviously. Alright, so we have been compute the Laplace sine of power function. Now let's proceed to the Laplace sine of cos 80. We have this function, then the Laplace sine of cos 80 mean from 0 up to infinity cos 80 e raised minus st. Now we'll prove, we need to compute this integration. Then we have to use the simple method. Obviously, it's free to apply other appropriate methods while you're calculating the integration of this. You can use byproduct or any forms of here. So here is I theta, we're using Euler's formula, cos theta plus I sin theta. If theta is represented by t, so we have this. So that if theta is EAT, so we cos 80 sin 80 we mean. So that from this Euler's formula tells the correlation between an exponential and the trigonometric function. So the real part of e raised it mean cos t, real part of e raised it mean, imaginary part of e raised it mean sin t. So we use Laplace sine of cos 80 in this definition back. So instead of cos 80, I can use real of e raised it. So it is minus st here, I will see itself. So we use, we can move out the real part, the women interpretation from 0 up to infinity. It is it is minus st here. Again, we have the same base, which should have to be sum of the exponents. So we have it is isc ia minus st dt. Again, we can compute using substitution technique, letting ia minus s with demi variable, so that you gain with this form infinity at 0, then you seek to assign specific value at infinity again at 0. The main little part of this is here. At infinity, this is 0. Again, at 0 is 1 ia. We multiply by its conjugate, we mean s plus ia, s plus ia. So we have little part of this mean s plus ia over s square plus 1, s square. Good. This is very interesting. So therefore, Laplace sine of cos 80 mean we would take the real part only from the previously we have here. So this can be decomposed as s over s square plus s square, ia over s square plus s square. Only we take the real part, so that we ignore the imaginary part. The imaginary part means the term stick with the complex number, where I mean square root of minus 1. I mean square root of minus 1. So Laplace sine of cos 80 is here. Again, Laplace sine of sin 80 mean from this we pick the imaginary term only. So the imaginary term. So finally we have Laplace sine of sin 80 is this. So specifically, if a is 1, if a is 2, if a is 3, we got these forms of integration. Thank you. Subscribe to get the next